session. And we have three speakers this afternoon: Emiliano, Ippoliti, Carlo, Cellucci, and Nickles. We begin with Emiliano Ippoliti, whom I know some because he studied for a few months at Pennsylvania State University. And before he came, I actually was reading in Italian his book on ambiguative inference. He and I and Carlo edited together a book called Logic and Knowledge, a collection of essays. It came out from Cambridge Scholar Publishing a year or so ago. Emiliano has lately edited a book on heuristic reasoning that came out from Springer this year, and a paper called The Dynamic Generation of Hypotheses. He's working on mathematics, finance,
Yeah.
and philosophy.
Yeah. You don't see the connection, I guess.
So, there you go.
Okay, thank you, Emily.
Yeah.
And in my paper, on my talk, I will examine former results in the process in knot theory and topology in order to shed light on the rational ways of advancing knowledge. To this end, I will focus on two problems. The first one is knot theory, and the problem is about how to tell knots apart. And that means the search for classification of knots and a complete invariant. And the second problem is about topology, is in topology. And the problem here is to find a way to tell surfaces or manifolds in a more general way apart. And I will focus on the construction process of the fundamental group. As we will see, these two problems tell stories of success and failure, or better, of partial success and failure. But I believe that we can learn a lot also from failures or partial failures, because even if an attempt does not solve the original problem, it reveals its inner dynamics. So let's start with the first problem. First of all, I will give you a brief reminder of what a knot is from a mathematical viewpoint. A knot is a simple, closed, non-self-intersecting curve in R3, something like this. And you can also count as a knot this one, which is called the knot. And the knot theory is simply the study of the behavior of knots under a specific kind of deformation, in particular ambient isotopy. That means that you can distort a knot, to stretch, pull, etc., without breaking it. So the main problem to solve, and I will not give you the entire story, but the main problem to solve is the determination of knot types and how to tell when two knots are equivalent under isotopy. That means that you have to solve the problem about telling knots apart, which in particular requires to distinguish non-equivalent knots, and so you have to produce a kind of classification of knots. And you must be able to assign the same quantity to equivalent knots, and that is the task of finding an invariant. And you should also be able to distinguish a knot from the knot. Now, classifying knots up to equivalence turned out to be a very hard problem. Maybe some of you know the story. The problem originated in 19th century theoretical physics. For Helmholtz, Thomson, Lord Kelvin, Maxwell, Tite. And maybe some of you remember Lord Kelvin's vortex theory. And the problem passed from physics to mathematics, and especially thanks to Peter Tait. And Tait put forward an extensive study and tabulation of knots in order to determine when two knots are different. That means isotopically different. His study ended up with the so-called Tait conjecture, which today have been all solved. So let's go back to the problem. How to tell knots apart? How to distinguish the knot from the other knots under this deformation? A basic strategy is the search for ways of associating a quantity to knots such that it does not change under the deformation, so isotopy, if the knots are the same. And that's what is called an invariant. So several approaches have been put forward in the last century. The first one is based on color, another one is based on numbers, another one is based on algebra, another one is based on graphs, and there are also other approaches. In my talk, I will focus on three of them: colors, number, and graphs, and I hope to cover the other approaches in the paper. These approaches turn out to be ways of interpreting and manipulating knots in a very specific way. And the interesting feature of knot theory is that different approaches reveal specific features of knots and specific features of procedures for unpreviewed knowledge. Well, first of all, even though we define knots as three-dimensional objects, knots are opaque to a lot of the tools developed for three-dimensional objects. So a lot of the approaches which we are going to see study the two-dimensional representation of knots. And that's why they search for the application of tools and knowledge to another domain to be imported into knot theory. So it's the applicability of tools and knowledge from other domains that motivates the choice of a particular representation of an object like a knot. So a key tool of problem solving in knot theory is change of representation, looking for new representation. In particular, representation by the so-called knot diagrams or projection into a plane. And here you can see an example of projection. So a knot diagram is the shadow of the knot plus the crossing information. So you have to encode this information. So a knot diagram is something like this. It's not simply the shadow. More formally, the projection is the image of a function from Rt to the plane, taking the triplo x by z to the value x, y. And the use of this representation allows us to employ tools and techniques and conceptualization for two-dimensional objects for knots, but also raises new problems. An example of new problem is that the same knot can be represented by several diagrams. It depends on the projection point. Here you have an example. These are two diagrams that are this projection of the same knot. So now the problem is that there is an infinite number of sequences of moves that you can form a diagram. And this is why it can be difficult to decide if the diagrams do or do not represent the same knot. So the use of particular representation generates a new problem. And so this leads us to several questions, like does the choice of a particular projection affect the result that we obtain, the formal result, or do they depend on this specific representation? And that's not an easy question to answer in knot theory. And we need a theory to be sure that we can avoid this problem. This is the right master theorem proved in 1927. And so we know that some results in knot theory are not representation sensitive. So this new two-dimensional, sorry, there is a typo, two-dimensional representation has the potential to solve the problem in the field, but it also raises new problem. So as we will see, different representation of an object highlights some of its characteristics and cut off deliberately other ones. So in a sense, you always win something and you always lose something. And I will try to give substance to this affirmation and what follow. So let's have a look at the first approach to this problem, the one using colors. It's not the first one in historical order, so I'm not giving them in historical order. Coloring is an approach developed for discrete mathematics, for example, to solve, to pose and solve the 4-color and 5-color theorems. And it was introduced in knot theory by Fox around the 60s, and was extensively used and popularized by Kaufman in 1991. What is coloring? Coloring is based on the assignment of distinct labeling, could be a color, a number, a letter, to each component of the entity you are trying to study. Something like this. So you can see what colors, numbers, or we don't have a letter here, okay. What's the problem here? That there are no components for knots. Because from a two-dimensional point of view, a knot is a single strand in 3D. And it cannot be discretized, so there are no other levels to be put on the knots. So in this sense, coloring is a no sense for a 3D knot. And they cannot be even defined for a knot in 3D. Okay, you cannot give only one color for a knot in 3D. But a knot diagram can be discretized. For instance, you can use 3-colorability or 5-colorability. Here you can see an example of a 3-colored knot. And a knot is 3-colored if every arc is colored, for instance, red, blue, and green, and at any given crossing, all 3 colors appear, or only one color appears. So the interesting features of this is that colorability provides a simple invariant. For instance, 3-colorability can distinguish kind of knots like the trefoil knots and its mirror image. Sorry, there's a typo without S. And the trefoil knot and the knot. And on the other hand, 5-colorability tells apart the figure 8 knot and its mirror image. But it does not work always. That means that, for instance, 3-colorability cannot distinguish the figure 8 knot and its mirror image, or figure 8 knot and the knot. And on the other hand, 5-colorability cannot tell apart the trefoiled and its mirror image. So, in this sense, it's not a complete invariant. There is no completeness. But it allows us to prove interesting properties about knots. The main result coming from Fox, is that every 3-color knot is non-trivial. If a given diagram can be 3-colored, we can say that it presents a knot other than a knot. It's a formal result. So since we can with certainty tricolor some diagrams, then we have just proven the existence of non-trivial knots. So tellingly, even though colorability cannot be defined for knots in 3D, 3-colorability turns out to be a property of the knot itself. not a property of the projection of the node. So the choice of a particular representation of node and its modeling by means of properties that hold only for it tell us something general about nodes in 3D. That's an interesting point of the use of color in node theory. So let's now have a look at the second approach, the one based on graph. As you probably remember, graph is a finite set e.g. of vertices and a finite set of edges, e.g. Any edge is paired with not necessarily distinctive vertices called endpoints of the edge. So it's something like this. And type itself was the first to connect dots and planar graphs. In effect, he noted that a projection of node on a two-dimensional plane divides the plane into several regions. So they color the regions of the node diagrams alternately with white and black, following listing, that's a technique of listing, and constructed the graph by placing a vertex inside its region, its white region, and then connected vertices by edges going through the crossing point of the diagram. So that's the result of this process. So even nodes on the left and the corresponding graph on the right. From this representation, we can express information also about crossing or not by means of the so-called signed planar graph. And this is what Tate did. And so we obtain this new graph from the node. So at the end of this process, we have a new object, the graph of a node. And it's the result of a very strong heuristic move which generates new information about node that we didn't have before the process took place. And from this representation of nodes, we have three main contributions to the study of nodes. The one is that, for instance, the formation of nodes, so their equivalence, is explained in a schematical way by graphical representation of nodes. The second one is that the graphical representation of nodes also made a contribution to the study of construction or union of nodes. And above all, this tool provides necessary and sufficient condition for amphibious nodes. It's a new result because of a new theorem, for instance, saying that if two node graphs G pi and G star pi are the same type and have the opposite signs, then the original node K of pi is amphibious. That is, K is equivalent to its mirror image. And these are the references. So we can see here that other tools and objects suggest specific procedure of operating over the elements of a problem, for instance, coloring the regions, and allow us to transform them. In that case, transforming a node into a planar graph. So in this sense, they generate new information which is not contained or even available at the beginning of the process. And the third approach to this problem is the one based on numbers. I mean, we can observe that a natural way of attacking the problem of equivalence and classification of nodes is to investigate their inner composition. So classifying nodes by finding a way to order them from the simpler to the more complicated and connected them by means of a suitable functional composition. Why is it important? Because if you succeed in doing this, you can factorize the nodes. And that what And this possibility of factorization was explored by Alexander and Briggs in a paper published in 2037. So this technique has the advantage that it does not require classification of all knots, but rather only those knots that cannot be made up of smaller pieces, so to say. So it draws on the natural idea of numbering knots in such a way as to conserve the composition into prime factors. So such a numbering, if any, would associate a prime number to a prime knot, a composite number to a composite knot, such that the prime factors of the number are the prime factors of the knots. So in this sense, number serves as a model for knots. So now the problem is there a way to see a knot in a number theoretical fashion? How to construct, if any, prime knots, composite knots, and composition itself? So that's the critical heuristic move we need to advance our knowledge. And if this move can be made, it generates new operators, identities for nodes. And moreover, we have a method for producing a classification, and in the best case scenario, a complete classification, a kind of arithmetics of nodes. And the idea of a number theoretical approach of node goes back to Gauss and was deepened, put forward by Schubert and Mazur. So, how to construct a composition for node? So the first observation is that the essential property of a node is not its manifold structure, under which every node is equivalent to a circle, but rather in its embedding into the empty space. So the connected sum of nodes require an elaborate definition that produces a well-defined embedding. And a possible way of doing this is cut its nodes at any point and join the boundaries of the cut, keeping orientation consistent. And so you have something like this. That's a possible way of connecting nodes. This sum is independent of the location of the cut. It generates non-new crossing, and moreover, it poses and solves problems in knot theory. For instance, by analogy with number, we can investigate properties like commutativity. It's one, obviously, and the answer is positive. Obviously, as you can see in the picture, nodes commute. And we also ask for associativity, again by analogy. And I will not give you the entire proof, but also in this case the answer is positive. And we can go on, we can ask for subtraction, and we have a difference here, this analogy, because we don't have subtraction for nodes, while instead we have subtraction for numbers. And we can also move to another question about inversion. What is an inverse knot? For a given knot, find another knot that composed with the first one gives you a knot. And in that case, like for natural number, the answer is no. For every natural number n greater than 1, there is a non-natural number m such that n times m is equal to 1. And so there is no general way to find a knot that composes another one, cancel them out. That means gives them nodes. So, but what about primes? So, as you know, prime number is one that a prime number is one that it's not the product of smaller numbers. So a prime knot should be one that is not the sum of singular knots. The interesting aspect of this investigation is that prime knot exists. There is a formal proof of it. In the picture, you can see some example of prime knots. And since we have an existing proof of prime knots, we can ask about factorization of knots. And this leads us to one of the main results in knot theory, which is super theory, 1949, stating that every knot can be unique way, decomposed in a finite number of prime knots. So the entire process ends up with a specific arithmetic of knots, which does not solve the problem of classification of knots in a general way. That means that there is no natural numbering of knots, because there is a lack of order in the set of nodes. Why? Because natural number have a total order that does not exist, or at least has not been discovered for nodes. Of course, it's common to order nodes by the number of minimal crossing on the diagrams, but its order is not linear. For instance, which of the following nodes with 7 crossings is the smaller? So at the moment we don't have a systematic answer to this question. Nevertheless, this arithmetical of nodes allow us to discover an important feature of nodes, namely the unique decomposition of every node in a finite amount of prime nodes. So before moving to the second problem, fundamental group, I would like to give you an example of the role of notation in knot theory. The interesting aspect here is that the seemingly simple and primitive act of notation is a way of creating knowledge. That means to create and import new knowledge in the field under investigation. And I will give you as an example the Cohen notation for nodes, which is the endpoint of a specific interpretation of nodes and of a heuristic approach of them. I start quoting Cohen himself, who states that in this paper, in 1967, we describe a notation in terms of which has been found possible to list all nodes of 11 crossing or less, and some properties of their algebraic invariance whose discovery was a consequence of the notation. So it's based on a well-known heuristics, the reduction of a global problem to a local one. So Conway used to investigate portion of nodes diagram, the so-called tangle. Tangle is a component of a knot projection with a circled region in the projectile plane, such that 4 strands exit the circled region. So you can see here simple tangles. So on the basis of a simple algorithm, Conway shows how to mirror tangles into numbers. That's an example of expressing tangles by numbers. That's the 2-3 tangle. So I will not give you the entire story, obviously, but you can obtain nodes from tangles. You just have to join the 2 northern and 2 southern strands together. So from the tangle you get this specific knot. And so at the end of this construction, we have a representation of nodes in terms of tangles. And so you can use tangles to investigate nodes. Now we have obviously a first problem here. So do different notation imply different tangles? The answer is no, unfortunately, because otherwise we would have a complete invariant. For instance, these 2 tangles are equivalent under headmaster moves. Here you can see the picture. 2, 1, 1 minus 2, 2, 1 which are two different notation, are the same nodes. You can switch the yellow part of the second node to obtain the first angle. So that means that notation is not a complete invariant, but from this, Conway obtained his most important contribution to knot theory. He focused on a specific subset of tangles, the rational tangles, the tangles that can be expressed by continued fractions. So continued fraction is something like this. Maybe some of you can remember of it. A continued fraction use the indexes in the Conway notation of two tangles to show that they're equivalent to one another. And Conway obtained a beautiful theorem saying that two tangles are equivalent if they have the same continued fraction values. For instance, you can show that tangles minus 2, 3, 2, and 3 minus 2, 3 are equivalent to each other, or you can show, for instance, that these two tangles are equivalent. Two very different notation. These two rational tangles, I mean. In fact, they have the same continued fraction value, 29/6. So now the interesting aspect of this use of tangles is that the same holds for nodes obtained by rational tangles. And so we can prove this theorem. All nodes obtained from a rational tangle are alternating nodes. So at the end of this construction, we have an algorithm able to distinguish equivalent nodes. And so Conway notation is the endpoint of a way of interpreting nodes. And it's a heuristic tool built in order to solve problem, in some cases pose problem. Again. So we can now face the second problem, which is the fundamental group and the construction process of fundamental group. And as I told you before, the problem is how to tell surfaces or manifolds apart. And so we have the determination of manifold types, so their classification, and how to tell when two manifolds are equivalent, so find the invariance. So the classification of two manifolds and three manifolds is a very hard problem again, since traditional tools such as Genus, orientability, and boundary components are not able to completely describe a three-manifold alike surfaces. So here, traditional invariants like Euler characteristics are useless for three manifolds, for instance. They all became zero. So we need a new invariant, to search for a new invariant. And this task was taken on by Poincaré, and he solved the problem using algebra. Why algebra? Why employ algebra? Because algebra is the study of structure, which means something preserved under specific function or operation. So now, the interesting aspect of the construction process of the fundamental group is that there are many possible ways to model topological space in order to be treated in algebraic terms. And fundamental group is the result of step-by-step construction that gradually introduce modification and new information into topology. And by new information, I mean new entities, new definition, operation, relationship. Now, there are many possible interpretations of the problem here. Obviously, as always, the data not only do not determine, but also do not seem to suggest an algebraic structure to be associated to a topological space. So, here the analogy with algebra is the key in the generation of the constraints for the solution of the problem. Constraints in Tom's terms, or condition of solvability in Cellucci's term. And the main problem, obviously, is how to define the topological counterpart of a set of elements of an algebraic structure, how to determine and define the topological analogous of a progression in algebraic structure. The first move is finding elements. And the elements are paths on the manifold. Here again, there are many possible ways of choosing elements. That's a possibility. For instance, we could start from this interpretation of a two-manifold, a surface. And it exhibits an algebraic structure, the set of all parts of a topological space with respect to the product. But it doesn't offer a lot for the solution of our problem. And here I'm quoting Fox and Crowell. They say that the meager algebraic structure of the set of all parts of a topological space with respect to the product is certainly far from being that of a group. So we need a better interpretation and manipulation of a topological space in order to solve the problem. And one way of improve the situation, I'm quoting again Crowell and Fox, from an algebraic point of view, is to select an arbitrary point P in X, where X is a topological space, and let's recover text on two paths which begin and end at P. And so that's a new interpretation of a topological space. So here we have that the product is certainly defined and is still a loop with the same base point. It has the identity path and a multiplicative identity. So the set of all P-based loops in X is a semi-group with identity. That means that there are no inversion. So here we have another problem because we need a richer algebraic structure in order to solve the problem. We need inversion in particular. So we had to have inversion, we had to introduce orientation for paths, for the loops. So the inverse of a loop is given by traversing it in the opposite direction. So summing up, we have that the elements of the group are oriented paths starting and ending at a given base point. These base points are necessary in order to make sense of the composition within topological entities. And the base points are the identity elements E or I. And orientation is needed in order to make sense of inverse. Inverse orientation on the loops define the inverse elements, and an element of the group is a class of loops. Two elements are different if they belong to different classes. And composition is the addition of loops, and it is associative but not commutative. So now we have an algebraic image of a topological object, and moreover, we have information about this topological object not contained in the topological space at the beginning. So the fundamental group is a nice example of a hybrid mathematical object in Emily terms. So it's the result of a new language and discourse about operations elements for surfaces under homotopy. And it allows us to tell manifolds apart by calculating their fundamental groups. For instance, you can tell apart sphere, angles, torus, etc. So the fundamental groups create a new representation of topological object which solves certain problems that we have seen and pose new ones. For instance, concrete conjecture solved by Berman, which can be posed because now we have the fundamental group. And the fundamental group can be also used in knot theory. It was used by Wirtinger in 1905 to solve problems in knot theory. So we have a problem here again that, quoting Crowell Fox again, that the algebra topology is only a partial characterization of the topology. This means that typical theorem of algebraic topology will read: if the topological space X and Y are homomorphic, then such algebraic conditions are satisfied. The converse proposition, however, will generally be false. Thus, if the algebraic conditions are not satisfied, we know that X and Y are topologically distinct. If, on the other hand, they are fulfilled, we usually can conclude nothing. So the bridge from topology to algebra is almost always a one-way road. But even with this, with that, one can do a lot. So I will finish my talk making some remarks on way of creating knowledge. The example outlined so far show interesting futures in way of advancing knowledge. The first one, the central role of construction and representation. These representations are basically a way of interpreting and manipulating a mathematical object that generates new information. And this way are suggested by problem to solve and existing knowledge. The construction of representation introduces knowledge and information not contained in the problem at the beginning. So, in order to create representation, we have to rely on comparison with existing knowledge. And the representation highlights certain features of the object and deliberately neglects other ones. In this sense, it's always partial and does not determine entirely or exhaustively our object. So, and that's why representation theorems, in a technical sense, are so important in mathematics. So they allow us to establish a fixed and well-defined relations between two different entities and to use one as a tool to investigate the other. A beautiful example in knot theory is Alexander's theorem in 1923, which connects braids to knots. So the second characteristic I would like to stress is the sensitivity to representation. Some results are dependent on the chosen representation and on the order of their introduction, the construction of the hypothesis. And this leads to a related problem, which is the historical nature of ampliation of knowledge. The representation that we can build depends on existing knowledge, and as new tools, viewpoints, and problems are generated, we can apply them to other fields to shed new light on it. So, as knowledge advances, new possibility of interpreting non-object emerge, and that generates new knowledge. Another important point is that notation, for instance, comments and definition. I didn't have time to do this in this talk. For instance, the Jones polynomial are interpretative and heuristic tools built to solve and pose problems. They are not mere stipulation, they are leading with imperative reasoning, and they are the end points and not the starting points of interpretation that introduce information into a domain. And in this sense, mathematical objects are inexhaustible as new viewpoint can always be offered. I'm following Carlo here. That's because the process of ampliation of knowledge multiplies the viewpoints and determination of an object, and this process is based mainly on analogies, because the analogies permits the construction of language, which ends up with a new categorization and conceptualization of the subject of the object under investigation. Yes, there is another objection to this viewpoint. That's my last few words. The first one is that analogies are bound to break down even if initially fertile. So they start from insight and ends up with nonsense. And the second objection is that rigorous interpretation and explanation are literal and not metaphorical. Here there are for instance, Bungen could be used to raise this kind of objection. Okay, I will skip the quotation, it's just too long. I will just state my point, which is that analogy is not a simply and static transfer of fixed knowledge from a source to a target. As I tried to show, in interesting cases, requires a dynamic process whereby the target has to be interpreted, changed, and manipulated in order to treat it in terms of the other and obtain new knowledge. So during this process, new information is gradually introduced in the target, and so it seems to me that the nonsense analogy is a nonsense, because we have no other options. So new is not an absolute concept. New is always compared to something known or familiar. So, and our inquiry cannot even begin without something already known, which we use as a basis for our investigation. So, I would endorse Tanner saying that analogies exist because of the way we categorize. So, the Bunge-style objection draws on a static conception knowledge, the object of scientific inquiry, because it draws on the idea that object can be determined in a complete fashion. They have a given exclusive set of properties. While I would argue that a dynamic conception knowledge and of its object is a more appropriate and effective way of making sense of the way we produce new knowledge, according to which new representation offer a person and open to new determination modeling of the object of inquiry, which gradually allow us to define the operators, the constraints, the problem space of inquiry. And I finished. I will just give a special thanks to Justin Roberts, which works at the Department for Mathematics at UC San Diego. His conversation with Eva inspired my interest in theory and topology. So thank you.
John Norton has on his Pittsburgh this enormous website.
Yeah.
Where, I mean, he likes to have fun with all kinds of things, but he has a draft of a book manuscript in progress called A Material Theory of Induction, where he actually starts off with a classification problem that you were talking about.
Yeah.
It was Marie and Pierre Curie, the crystallized radium, and how to classify it, how to distinguish it from other crystalline forms, and so forth. And, so for one thing, you may not have seen it, and it would be, I think, interesting to you.
Yeah, to look at.
Yeah, because one question, your examples are mathematical. But
Yeah.
don't you think the same kinds of operations, same kinds of things would apply also in the empirical world? And John's conclusion with his material theory is that there's no special method here, that it's the facts that emerge from all these different. So roughly the idea is we try to develop tools, more and more precise tools that we can use to transform these objects in different ways, and then look for invariances, as you were saying, and then from that, new bodies of facts emerge, and new theorems and involving a new language can come out. Does that sound like it transfers to the empirical?
Yeah, I think so. I mean, yeah, there are complications because physicists are, for instance, I guess you mean physics. Physics would say that it's hard to believe that different representation of the same object. For instance, I think of quantum theory. We have different formulation of the theory with different formalisms, but in a sense they describe the same object. So I intended to be so. But I believe that also our understanding of empirical world and nature cannot avoid this problem, because at the end we are human beings, and we can only have a human representation of
I suppose the issue goes back to Locke's idea that we have no real classification of nature.
Yeah.
To some degree, or at least our human classifications are always subject to challenge by the future.
Yeah, because,
So it's
because the kind of nature.
nominal classifications, human elements of what we're doing.
Yeah, but I mean that it works well for mathematics. I mean, a lot of discovery in mathematics has been put forward, in my humble opinion, in this way. So behind the scene, the work of mathematicians heavily informal, interpretative, and in this sense, in my opinion, it seems that not theory and topology are really a kind of open laboratory where you can see what happens behind the formalism, because you have to try a lot of things to obtain, in many cases, also small and partial results and formal results. And different viewpoints sometimes converge and sometimes doesn't converge. So, you have a question for me?
It's related to that. What you said at the end of your talk is these mathematical objects are inexhaustible.
Yeah.
That is,
And
you can approach them by inventing different representations, different notations. Each one will give you some information about them, but it doesn't exhaust them.
yeah.
There is always something left. Now, that suggests to me that mathematical objects have to be distinguished from any of our representations of them, which suggests to me a kind of Platonism about mathematical objects. And I don't know what some other word to use, because it's not like I want to invoke the Platonic heaven. I don't, but I keep coming back to the very strong sense, the more I work in philosophy of mathematics, that mathematical objects are independent of discourse. They are not a kind of discourse. They are something. And they are what they are. And there's always something more to find out about them.
Yeah, you mean that? No, I don't get
I mean, so,
the objection.
so what I gather from what you're saying is our knowledge of them is always incomplete,
Yeah,
and therefore, to be revised. But we never exhaust them, which suggests to me that they are what they are, independent of what we say about them.
yeah, maybe this person, they are what they are. That it's difficult to because
So we have something like a Platonism without being dogmatic about truth.
yeah, I mean, what they are at the end is not so important because I mean.
But what's important is their inexhaustibility.
Yeah, I mean, because they solve problems. They provide a part of knowledge about a specific problem. But what, for instance, what a circle is, I mean, it's not
My
important.
favorite example of the inexhaustible.
And that's why that's why I mention it.
Yeah.
Because I mean, what is a circle? Topological object, an algebraic object, a physical object. You can build, no, physical no, but geometrical in terms of elementary analytical geometry. They are all part of this object, and as new knowledge is built in other domains, can be related to a circle, whatever it is.
Then why do some domains of mathematics, or any domains, well, something about math, why do they seem to be more or less completed? David Hilbert, for example, once left the field of invariant theory when he thought he solved the fundamental theorem of that area, so moved to what he regarded as greener pastures. Why aren't the pastures ever green? Frontiers of discover inexhaustible? Why do branches become not useless, but dead in the sense they're no longer centers of what research activity? That's a good question.
That's a good question.
Yeah.
We have one question.
Yeah, from
Yes, yeah, sorry I interrupted.
Given that the discussion has taken this metaphysical turn, I'm not afraid to ask this maybe crazy question. So I couldn't quite sort of make metaphysical sense of the idea that tree colorability, for example, would be a property of the knots itself. I mean, I think that's what you said.
No, I said that tree colorability cannot be defined for three-dimensional object because you can.
That's right.
That's right. But
Yeah.
if you
When you project.
you project,
Yeah, right. So on the projection
you can define and
yeah. And then I thought you came back and you said that by doing the projection and studying these things in 2D, we learn that there is a sense in which tree colorability or otherwise is a property of the knot itself. I think you said that.
yeah. I'm saying
And that's
that.
what I'm sort of wondering how to think of that, how to think of tree colorability as a property of the object itself, as opposed to being a property of this much larger mathematical domain that includes the projection functions and the rest of it. It's a tree colorability would be a property of the knot and all the other mathematics that goes into your
Yeah.
projection.
Thanks for the question. Because it's a point. What I'm trying to say in that is the following. The choice of a representation is necessary in that case because if you want to use the three-dimensional techniques and tools available at the time, you can get a lot from the study of knot theory. You need to approach the problem with other techniques, coming, for instance, from two-dimensional geometry or for discrete mathematics. You need a new representation that can relate the knots, for instance, with the two-dimensional results, the results about two-dimensional objects. The representation, the knot diagrams serve this purpose. I don't know how to approach the problem. So let's see if choosing one representation like a knot diagram and applying to the knot diagram some technique that can be applied to a two-dimensional object, I find something that can be useful for the understanding of the original object, the three-dimensional object. The tricolorability do this because it tells apart some nodes from others, and but obviously it's not a complete invariant, so it doesn't solve the problem in the whole generality, but gives you important information about some properties of the nodes.
Some properties of the 2D representations of the knots, which are different mathematical objects.
But it says that you cannot, using right master theorem, which says that, which is important because it tells you when two diagrams are equivalent, using three fundamental moves, known as right master moves. So if I can say something about the projection, for instance, that you can distinguish these two, the threefold from the unknowns. You're saying that also in the three-dimensional space, the embedding of a threefold knot, for instance, is different from a circle in a space. So it's about.
So let's have one more question.
Yeah,
And then.
the time is over. Yeah.
Okay, so yeah, for the topic, lots of interesting stuff I I don't really have a question, more of a suggestion or invitation to comment. So all this stuff about modeling one domain through another domain. So you presented about knots, which is very interesting, as I said. But I was wondering if this idea isn't actually older. Isn't Descartes who was modeling the plane geometry, like the two-dimensional through
That's the same idea.
yeah. So I think There are historical rules.
Yeah.
The same.
I didn't have time to mention it. But it's elementary.
And then there's Renaissance painting.
Oh, yeah.
Yeah, so,
Yeah.
and that was in fact with the car, which was a very important tool to solve problems which were untractable using typical sort of geometrical
Yeah.
methods. And
Yeah, I mean, any algebra in that case,
Yeah,
to make
exactly.
sense of geometrical object. In that
Yeah.
case, with matrix. In that case, without matrix, because topological object is only about relative positions.
Yeah.
So I don't need matrix. So, thank you.
Yeah,
for-
that's,
Look, time is over, so I don't want to. Okay, thank you. There's a little change of the program because the bar is closing at 5 o'clock. So it's better to have the break now and 20 minutes of break, and then we have to do last talk of the
Mi sa che questo qua, no.